Welcome to The Explainer. Today, we're going to get our hands dirty with a classic problem from one of the most notoriously difficult physics textbooks ever written. It's a real rite of passage, and trust me, we're going to break it down and make it look easy.
So, our challenge today comes from this book, i.e. Irodov's Problems in General Physics. If you've ever studied physics, you've probably heard the legends about this one. It's famous for problems that don't just test if you know the formulas, but if you really understand the concepts. And problem 1.15? Oh yeah, it's a perfect example.
Here's the setup. We've got an elevator moving up with constant acceleration. After 2 seconds, a bolt just lets go from the ceiling. We need to figure out how long it takes to hit the floor and how far it actually traveled. Sounds simple enough, right? But that constant acceleration of the elevator is what makes this so tricky.
At first glance, this can look a little intimidating. You got multiple things moving, one of them accelerating. Where do you even start? Well, don't worry. There's a secret weapon in physics that can make seemingly complex problems like this surprisingly simple. So let's dive in. Okay, so here's our game plan. We'll set the scene, talk about this idea of choosing your perspective, solve it from inside the elevator, then solve it again from the ground, and at the end, we'll talk about what this all really means.
All right, the real key to cracking this problem isn't about finding some obscure equation. It's all about choosing where you stand to watch the action unfold, and our secret weapon for doing that is something called a reference frame.
So, what is a reference frame? Well, it's basically just your point of view. It's the where from which you measure everything. Are you standing still on the ground, watching the elevator zoom past, or are you inside that elevator, moving right along with it? That choice, as you're about to see, changes everything.
So we've got two main choices here. We can use the ground frame where we're stationary. From there, the elevator is accelerating and the bolt does this weird little dance where it moves up and then down. It's complicated. Or we can hop into the elevator frame. From inside, the ceiling and floor aren't moving relative to us, and the bolt, well, it just falls straight down. See what I mean? One of these is way simpler.
So let's start with the easy way. We're going to jump inside that elevator car and solve for part A, the free fall time.
Okay, once we're in the elevator, things get a whole lot clearer. To us, the bolt just has to fall 2.7 meters. Its starting speed relative to the floor below it is 0. The only catch, and this is the cool part, is that because the elevator is accelerating up, it feels like gravity is a bit stronger. So we have to add the elevator's acceleration to the acceleration of gravity. That gives us an apparent acceleration of 11 meters per second squared.
And with that little trick, the math suddenly becomes a piece of cake. We just grab a basic kinematic equation for falling objects, rearrange it to solve for time, and then plug in our numbers, the height of the car and that new apparent acceleration we just figured out.
And there it is, 0.7 seconds, just like that. This is the perfect illustration of the power of choosing the right frame. We got the answer to part A in just a few simple steps, and the best part, time is universal. It doesn't matter where you're watching from, that bolt is in the air for 0.7 seconds, period.
Okay, part A is in the bag. Now for part B, we need to find the bolt's displacement and the total distance it traveled. And to do that, it's actually easier to switch our perspective and watch from the ground.
So now we're standing still on the ground watching this all play out. The bolt's acceleration is just good old gravity, negative 9.8 meters per second squared. We already know it's in the air for 0.7 seconds. But here's the crucial detail. When the bolt lets go, it doesn't just start falling from a standstill. Nope, it was in an accelerating elevator, so at that exact moment it has an initial upward velocity of 2.4 meters per second.
So first, let's find the displacement. Now remember, displacement isn't the total journey, it's just the straight line distance from the starting point to the ending point. We can find this with another standard kinematic formula, plugging in that initial upward velocity, the time it was in the air, and the acceleration due to gravity.
And the answer is negative 0.7 meters. Now don't let that negative sign throw you. All it means is that after its little trip up and then down, the bolt ended up 0.7 meters below where it first detached from the ceiling. But hang on a second. Does that mean it only traveled 0.7 meters? No way. Remember, it started by moving up for a little bit before it started falling down. So the actual path it covered has to be longer than that. So how do we figure that out?
Well, to get the total distance, we have to break its journey into two parts. First, we figure out how far it traveled upward until it reached its highest point. Then, we calculate how far it fell all the way from that peak down to the elevator floor. Add those two distances together, and that's the total path it took.
And when you run the numbers, you find that the total distance the bolt traveled on its little adventure was 1.3 meters. And there you have it, the final piece of the puzzle.
So let's just put this side by side because it's a really important idea. Displacement is the as the crow flies measurement, just where you start versus where you end. But distance covered is the total length of the path you actually took. This problem is a perfect way to see that difference in action. So, what did we actually learn here, besides just the answers to a tricky physics problem? Let's zoom out and look at the big picture lesson from this falling bolt.
This table tells the whole story, doesn't it? To find the freefall time, jumping into the elevator's reference frame was a no-brainer. It made the problem incredibly simple. But to find displacement and distance, we needed that bird's eye view from the ground. The lesson: there's no single best perspective. The right one depends entirely on what you're trying to figure out.
And that really is the big idea here. One of the most powerful tools you have in physics isn't some complex formula or a supercomputer, it's just your ability to change your point of view. By shifting into an accelerating reference frame, we turned a complicated motion problem into a simple one. This isn't just a trick, it's a fundamental strategy in physics.
And that kind of makes you think, doesn't it? This idea that you can gain total clarity just by changing your perspective goes way beyond a single problem in a textbook. So I'll leave you with this question. What other problems, maybe in physics or maybe just in life, become a whole lot simpler if you just decide to look at them from a different angle?